Hello, everyone, and welcome to this explainer. Today, we're unlocking something that is absolutely foundational to modern technology, yet it's completely hidden from the everyday consumer. We are talking about UVM, the Universal Verification Methodology. Now, if you've ever found yourself wondering how engineers actually guarantee that incredibly complex silicon chips, the ones powering your smartphone, your car, those massive AI servers, how they guarantee they actually work before they're physically built, well, you are in the right place. We're going to demystify exactly how these complex chips are tested, and I promise you the architecture behind it is absolutely fascinating.
Okay, let's dive right into this. Here's our roadmap for today's explainer. We'll kick things off with the chaotic history of early chip design in Section 1, the verification chaos. Then, we'll hit the birth of an industry standard, before really digging into the architecture in Section 3, inside the test factory. After that, we'll cover agents of verification, execution flow, and wrap it all up with why UVM rules today. All right, Section 1, the verification chaos. Let's talk about the fragmentation in the early days.
To truly appreciate the elegance of UVM, we kind of have to set the stage in the early days of semiconductor design. Back then, exploding chip complexity was creating an absolute verification nightmare. So picture this. In the 1990s, verification engineers relied on just plain Verilog test benches. And they were simple, sure, but they were incredibly hard to scale as chips got bigger and bigger. Then, early 2000s, we see the rise of HVLs, or hardware verification languages, like System Verilog and SpecMin-E. Now, these were major game changers, mostly because they introduced object-oriented programming to hardware testing. And that naturally led us to the mid-2000s, where more structured methodologies like VMM and OVM emerged. But as we're about to see, this rapid, wild evolution created a massive roadblock.
So, here's where the drama really starts, the clash between these methodologies. On one side, you had VMM, the Verification Methodology Manual. This was developed by Synopsys, based on System Verilog, and it was super powerful, but it was proprietary. On the flip side, we had OVM, the Open Verification Methodology. This one was developed collaboratively by Cadence and Mentor Graphics. It was open source, much more flexible. The problem? VMM and OVM were completely incompatible, literally couldn't talk to each other. This threatened to totally fragment the entire semiconductor testing industry. It meant a test bench written for one tool couldn't be used on another. The industry desperately needed a unified solution.
Which brings us to Section 2, birth of an industry standard in unifying the verification world. Enter the hero of our story. The industry finally woke up and realized that fighting over methodologies just wasn't helping anyone. So in 2010, an organization called the Accelera Systems Initiative stepped in and led this massive, unprecedented industry collaboration. Competing companies actually sat down at the same table. And the incredible result? Boom! UVM 1.0 is officially released in 2011. And this wasn't just a flash in the pan, right? By 2017, UVM was formally adopted as IEEE Standard 1800.2. That officially cemented its place as the undisputed global standard. Now, what's truly impressive is exactly what UVM set out to achieve. The core goals were, number 1, standardization across all tools and companies. Number 2, creating a completely vendor-neutral methodology. And number 3, maximizing the reusability of verification components. UVM was essentially this standardized, highly upgraded version of OVM, built right on top of System Verilog. The whole idea was that an engineer could build a test component once and then reuse it across multiple projects, completely regardless of whether they were using Synopsys, Cadence, or Mentor Graphics tools. A real game changer. All right, let's open the doors in Section 3, inside the test factory. The UVM mental model. Now that we've got the historical context down, let's look at the actual technical architecture. And we're going to use this brilliant mental model. I absolutely love this quote. Think of UVM like a test factory. Keep this in your head as we go through these next few slides. Because instead of just typing out raw lines of code, with UVM, you are effectively building a factory. You've got different departments, assembly lines, specialized workers, and the whole shebang is dedicated to one thing, finding bugs in your chip design. Let's walk through the top-level hierarchy of this factory. At the very top, you have the test. Think of this as your factory manager. It's the big boss, the top-level controller that configures everything and decides exactly which scenario we're running today. Right below the manager is the environment, or ENV. This is your main container, basically the actual factory floor where all the verification components live. Then we have our quality control departments.
The scoreboard compares the expected results against the actual results to spot any functional mismatches. And finally, the coverage collector. You can think of this one as that slightly annoying auditor walking around with a clipboard, micromanaging the floor, just making sure absolutely every scenario we planned for has actually been tested so nothing slips through the cracks. Let's map this out even clearer, because this illustrates brilliantly how the core UVM components map directly to roles on a factory floor. The sequences? Those are the engineers brainstorming and creating the test ideas. The driver is the heavy machinery actually applying those test ideas directly to the chip. The monitor is the sensor, quietly observing the results of what just happened. And like we just said, the scoreboard is the ultimate judge, determining if the results are actually correct. It's a highly structured and just incredibly organized way to test software and hardware. Moving right along to Section 4, Agents of Verification. Let's hit the assembly line. Let's zoom in a little closer on that factory floor and look at arguably the hardest worker in the environment, the agent. An agent is basically a component that models a specific protocol interface. So, for example, if your chip communicates using AXI or SPI, you just drop in an AXI agent or an SPI agent. The true superpower here is reusability. Because it's fully standardized, you can take an agent you built for Project A and literally drop it seamlessly right into Project B. It is the ultimate plug-and-play verification component. So, if we pop the hood, what is actually inside this agent? Well, it's got three primary subcomponents. First up is the sequencer. This generates and controls the stimulus sequences and then hands them off to the driver. Now, the driver's job is absolutely critical. It receives these high-level transactions and converts them down into the gritty, physical, signal-level activity that the design under test, or the DUT, can actually understand. And meanwhile, just sitting off to the side is the monitor. It's passively observing the signals coming out of the DUT and translating them back up into high-level transactions so the scoreboard can evaluate them. Real quick terminology check here, because this is pretty crucial to understand. The sequencer deals in sequences and sequence items. A sequence item is just a single transaction. Think of it like one single data packet, or just one instruction. A sequence, on the other hand, is a complete set of those transactions that make up a whole test scenario. So, a continuous stream of packets being fired at your chip over and over. That entire stream is a sequence. Okay, Section 5, Execution Flow and Communication. How do we actually run this factory? So we know what the machines are, but how does this entire factory actually power up without causing massive chaos? Well, UVM brings order to the simulation process through a very strict phasing mechanism. You can't just flip a giant switch. The factory powers up in exact, deliberate steps. Step 1 is the build phase. This is where all components are created and configured. You literally can't run anything until the factory is fully built. Step 2 is the connect phase, where the communication ports between all those components get hooked up. Step 3 is the run phase. This is the main event. The actual simulation happens here, and stimulus is driven into the chip. And finally, Step 4 is the extract and report phase, where we sweep up all the data, collect the results, and print out those all-important pass-fail summaries. Now, during that connect phase I just mentioned, we're hooking up communication ports. UVM uses something called TLM, or transaction level modeling. And here's a massive takeaway. This simply means components communicate using transactions, not individual pin signals. Instead of the sequencer telling the driver, hey, toggle wire A high, wait a clock cycle, then toggle wire B, it just hands over a single transaction that essentially says, send this data packet. The driver handles all the messy signal toggling on its own. This super high level of abstraction, that is the secret sauce to UVM's massive reusability. Powering all of this under the hood are a couple of really advanced, heavy-duty, object-oriented software concepts. First is the factory pattern. Honestly, this is a programmer's dream. It allows verification engineers to dynamically replace components without having to rewrite or modify any of the underlying test bench code. Need to swap out an old driver for a new one that intentionally injects errors? You just tell the factory to substitute it. Done. Second is the configuration database. This lets you pass parameters and settings cleanly across the entire factory hierarchy, which completely avoids the absolute nightmare of hard-coding values. Finally, Section 6, Why UVM Rules Today, the Dominant Standard. We've seen the history, we've explored the architecture, but what is the real-world payoff of all this structure? Well, UVM has completely won the industry over. It is the dominant methodology for verifying both ASICs and FPGAs. Because of its highly scalable architecture, it's designed specifically to handle those incredibly complex system-on-chip, or SoC, designs. Its modular nature promotes seamless team collaboration. Seriously, one team can build the Axie agent, a totally different team can build the scoreboard, and they all snap together perfectly at the end. And most importantly, circling back to its founding goal, it works universally across the major EDA tools from fierce competitors like Cadence, Synopsys, and Mentor Graphics. Which means, practically speaking, UVM is powering your modern life. It's the framework currently verifying the chips going into all our consumer electronics. It's verifying the incredibly critical safety chips in automotive advanced driver assistance systems. You know, self-driving cars. And it's testing the massive next-generation AI and machine learning accelerators. Without the highly structured test factory of UVM, bringing these crazy complex technologies to market reliably, it would be virtually impossible. But that leaves us with a pretty fascinating thought to end on today. We've gone from plain Verilog in the 90s to the incredible unified standard of UVM today. But as chips like AI accelerators become exponentially more complex, we're talking featuring billions of transistors and totally new mind-boggling architectures, what methodology is going to have to evolve next to test the seemingly untestable? UVM completely solved the fragmentation of the past, but the future of verification? It is really just getting started. Thank you so much for joining me on this explainer. Keep learning, and I'll see you next time.